Proceed to the second part of my talk. And so the second part is meant to be like a toolkit for proving limitations of the expressive power of logics. So here we saw data log is strong. We saw that with some logics you can describe some computations. And here I want to show you what kind of tools are there for proving that something is not expressible in some logic. And we already saw such a tool for data log. We saw that if you want data log on arbitrary databases, you have this closure under homomorphisms, and then you can, closure under homomorphisms is the tool for proving that something is not definable by data log. Actually, it's interesting to try to understand why does this closure under homomorphism don't prevent this Immer-Manvadi thing and the simulation lemma. And that's because if you look at a string representation and you apply a homomorphism to the string representation, the only way of getting a new string representation is that you don't mess with the successor and the min and the max. So you can just rename numbers 0, 1 up to n-1 into other numbers, but you still get the same thing. So their homomorphisms just can't be used to produce counterexamples because you don't speak about string representations after applying real homomorphisms. Okay, so and don't get confused about this number 37 and this. I have a large number of sections. I want to tell you the first 4 or 3.5, and whenever it's 12:20, I will stop. So Jean-Éric, I regret here is algebra, but I probably won't have time to tell much about algebra. But the stuff about algebra is citing your work, so it's nothing new for you. Okay, so in this talk again, if in doubt, we talk about finite directed graphs. Notation is practically the same. Sometimes in the graphs, the nodes are also labeled. We already have seen what a graph property is. That was the starting point of the first part of the talk. Now, what is a k-array graph query? So Q is a k-array graph query if the following is true. Whenever I have an isomorphism pi between two graphs G and H, then for all k tuples of nodes of G, this k tuple belongs to the query result of Q on G, if and only if, well, if I move from G to H, that's the isomorphic copy, and pi is the isomorphism, then I just have to rename the entries in this k tuple according to the isomorphism, and I get a k tuple in the result of the other query. So this here means graph queries are closed under isomorphism. Okay. And now you know logics expressing graph properties or queries. Here's just 2 examples. The query which tells you that, or which returns all nodes x that lie on a triangle. You can express it like this. X is in the query result if there exists node y and z such that they form a triangle. Then we can discuss if these nodes must be pairwise distinct, and you can add this in first order logic. Or in existential monadic second order logic, which is a subclass of existential second order logic, you can express 3-colorability of graphs. And that's essentially just by writing down the definition of 3-colorability. So that's a generic formula. Okay. But how can we prove that certain properties are not expressible in a particular logic? And there is a huge toolbox that people have developed. And if you look in the books on finite model theory, you find Ehrenfeucht-Fressé games, you find locality results, you find 0-1 laws. So these are the classic things that are covered. And then you find maybe lots of related stuff. So if you have read Leonid's book, I won't tell you much that's new for you, but a little bit maybe. Okay, so let's look at 0-1 laws, because from my point of view, somehow that's the weakest formalism, but it's for showing non-expressibility, but in some cases it's really elegant. So what is a 0-1 law? So let's look at a graph property P. And then for a number n, I say mu n of P is the probability that a graph chosen uniformly at random from the set of all graphs on n vertices has this property P. So maybe you want to restrict attention to, so that you don't have this infinite set on graphs on n vertices. You just fix the vertex set to the set 1 up to n, and then you check how many graphs on this vertex set have the property and how many don't, and then you compute this ratio. And then the asymptotic probability of this property P, it's written as mu of P. That's just the limit of these probabilities and the limit for n going to infinity. And this limit may exist and it may not exist. But so in some cases mu of P is undefined. And now a logic is said to have the 0-1 law is if every graph property that's definable in the logic, for every such property, this asymptotic probability, so this limit exists and is either 0 or 1. Which means if you choose a large enough random graph, then you know almost every graph that you choose will have this property, or almost every graph that you choose will not have this property. And 0-1 laws are known for quite a number of logics and quite a number of special cases, but the two things that one should know is first order logic has the 0-1 law, and infinitary logic with finitely many variables has the 0-1 law. So if you look at first order logic but allow infinite disjunctions and conjunctions, but you just allow it to use a finite number of different variables, this logic has the 0-1 law. And what is nice about this is that fixed point logic, so least fixed point logic, but also partial fixed point logic. So that is the logic where on ordered structures you can simulate p-space computations. If you are on unordered structures, also these two fixed point logics have a 0-1 law because you can embed them into infinitary logic. And to give you a few examples, so the property of having an even number of nodes or edges is not definable in a logic that has a 0-1 law. Why? Well, even number of nodes, that for this the limit doesn't exist because it always oscillates between yes and no. Even number of edges, well, if you choose a graph, a random graph, about half of the graphs you choose will have an even number and the other half will have an odd number. So the asymptotic probability will, for even number of edges, will be 1/2. So not 0 or 1. So from that you immediately get that even number of nodes or edges is not definable in all these logics that have a 0-1 law. But there are properties whose asymptotic probability is 0 or 1, but which cannot be expressed in first order logic. So connectivity. If you choose a random graph, the probability that it is connected is 0, I would say, or almost 0. but still it's a property that cannot be expressed in first order logic. So this tells you the limitations of this tool of 0-1 laws. So if you're lucky, you can use 0-1 laws for non-expressibility. If not, well, you have to think of something different. And something different are Ehrenfeucht. For connectivity? But don't you have you isolated nodes? But how does the random graph look like? I think it has one giant component and then lots of other unconnected components. That's
assumed because you say because you look at uniform probabilities, right? So yeah, if you start throwing like a probability depends on number of nodes, that's totally different story.
That's
uniform. No, I can give you a description of this graph.
Yeah.
I mean, the set of in the infinite case, the set of nodes is all natural numbers, and if you edge between I and j, if j is divisible by the i's prime, or the other way around. That's your other graph. That's your other graph. Yeah, it's connected.
And in any case, random graphs
So-
are expanders, right?
So
They must be highly connected.
okay. So my point wasn't that it's a particular number. My point was that it's one of the numbers 0 and 1. So and then when yeah. So I know that in my lecture I did this computation from scratch, counting how many graphs are there on n numbers and how many are connected and so on. And I know that you get one of these two as a limit, even without citing expanders or nice stuff. But okay. So 0-1 laws are a tool, but for some properties you can't use 0-1 laws to show that they are not expressible in some logic. And Ehrenfeucht-Fressé games are a tool that is complete in some sense with respect to first order logic. So if something is not definable in first order logic, then there must exist an Ehrenfeucht-Fressé game proof of this. And who of you is familiar with Ehrenfeucht-Fressé games? Okay, who isn't? Okay, then I'm telling this for you. If now everybody had said, yes, I am, then I would have skipped this stuff, but it's worth doing it. So what are the games like? You have two players, which are called spoiler and duplicator, and the game is played on two graphs. So for the start of the game, you have two graphs, and you have two players, and you fix a number r of rounds in which you play. And let's say these are the two graphs we look at. And when you want to view these as directed graphs, you have edges in both directions. And so every player can play on, so this is the board, the two structures together. And in each round I, so you have r rounds, in each round I, you play as follows. First, the spoiler chooses a vertex in one of the two graphs. Let's say here he chooses B1. And then duplicator chooses a vertex in the other graph. So here, duplicator chooses A1. And then the next round begins, and spoiler chooses a vertex in one of the two graphs. Let's say he chooses in this graph. We call it A2, and duplicator answers with a vertex here. And in the third round, again, spoiler chooses in one of the two, and then duplicator chooses in the other one. Now let's say we played r rounds. R is 3 here, and now we want to check who has won the game. And what we do is, well, in r rounds, the two players have chosen vertices A1 up to AR in the first graph, and B1 up to BR in the second graph. And now who has won? What I do is I build the induced subgraph on the chosen vertices. So what does this look like here? I have just this node as an isolated vertex, and then I have an edge between A1 and A3. And here I built the induced subgraph on B1, B2, B3. So that's just this path here of length 2. And then I check if the mapping that maps AI to BI is an isomorphism on these induced subgraphs. So I don't check if the induced subgraphs are isomorphic, but I check if the mapping that the two players have constructed is an isomorphism. So what is it like here? Well, it is not, because here I have two components in the induced subgraph, and there I have a path. And the rules say duplicator wins if this mapping is an isomorphism. So here the duplicator is lost. And well, if we look at a different play on the same two graphs, if you have 2 rounds, what would duplicator do to win? So that's my first graph, and that's the second graph. And I would like to find 2 people who are not familiar with Ehrenfeucht-Fressé games to play this. So is there, okay? You want to be duplicator or spoiler? Duplicator? Okay, we say 2 rounds. Is there another volunteer for being the spoiler? Okay, good. So we play 2 rounds and spoiler starts.
Okay, well, I've lost, right? So I can just play at random.
So you check you choose some node.
The top left corner.
The top left corner.
Oh, this one.
Okay. Yeah, you have to, doesn't matter which one. And
yeah, the one just below A1.
you take this one. And what will you do if you just take this one? What would duplicator have done if spoiler chose something that's not directly connected? Well, he would have chosen that one. So what about 3 rounds?
So the top left also.
Take the top left. Well, you choose whichever.
I try the chain one.
You take this one or that one? The one? Or no, I didn't understand which one you want to take.
No, okay, yeah, the right one.
The right one. So you take this one,
Yeah, and then the one below.
and then the one down there, and that's A3, and then you have no chance. And if you check all the possibilities, you see in 3 rounds, spoiler has a winning strategy. So I have this here. So I write this here, A and B are equivalent if the duplicator has a winning strategy. And to make sure that you get an idea of this thing, let's look at one more example. So we have this, and we have, let's say that. How many rounds does spoiler need to win? And you see, if you have sufficiently many rounds, as long as the 2 graphs are not isomorphic, spoiler has a winning strategy. Now I want to find the smallest number of rounds such that spoiler has a winning strategy. What do you do?
Take the center on there.
Take the center. Okay, then I take any one here. And the opposite corner here. So here it's when you switch from one structure to the other, And there you have two that are not connected, and here this is connected to everybody. So what you have here in my notation, that on these two graphs, duplicator does not have a winning strategy in 2 rounds.
If I stayed in A, I chose the 2 leaves, the 2 top.
Yeah, but you would need one more round, wouldn't you? Okay, and now the Ehrenfeucht-Freyset theorem tells you that for 2 structures A and B, duplicator has a winning strategy in R rounds if and only if A and B satisfy the same first order sentences of quantifier depth at most R. And so one direction of this is quite easy. Namely, if there is a first order sentence of quantifier depth at most R that's satisfied by A but not by B, you can use this sentence as a description of a winning strategy for spoiler in R rounds, because spoiler just plays according to the quantifier structure of your sentence, which distinguishes between the 2 structures. And then the other direction is a bit more work. But what does this theorem tell you as a corollary? If you want to prove that some graph property P is not first order expressible, then what you can do is you can try to find for every number R graphs AR and BR such that the duplicator has a winning strategy in the R round game on these 2 graphs, but one graph has the property and the other one doesn't. And why will this here tell you that the property is not expressible? Well, if it was expressible, it was expressible by a sentence that has some quantifier rank, and this contradicts that. And that's the structure of most of the proofs where you show something, where you use Ehrenfeucht-Freyset games to show that something is not expressible. And, well, for example, the property of being a linear order of even cardinality is not first order expressible. Why? Well, for every number R of rounds, you choose 2 linear orders which are sufficiently long. One should have even cardinality, the other shouldn't. And then you construct a winning strategy for the duplicator on these 2 linear orders. And as long as they are sufficiently long so that in R rounds you can't spot the difference, you can have a winning strategy. And then writing down this winning strategy is a bit of work, but it's a nice exercise of doing this. And the length of the 2 linear orders needs to be bigger than 2 to the R if you want to survive R rounds as duplicator.
Is this theorem valid for every signature of the structure, the logic, and every sigma structure?
Yes, and it's not limited to finite structures. Well, it's you have to be careful about what the size of the signature is. So I always think in terms of finite signatures. So, but okay, what are further examples where Ehrenfeucht-Freyset games are used? So this is an easy exercise. This here is something that's a bit more difficult. That connectivity of graphs is not expressible in existential monadic second order logic. So that's a proof where you have to choose graphs in a suitable way and then look at colorings and so on, and in the end you again play an Ehrenfeucht-Freyset game in R rounds. And there also, if you look at the literature, I think Fagin's original proof is very long and very complicated, and then a couple of years later he published another proof which is much shorter and much more elegant. and essentially in the first proof, the games made life difficult because things were quantified in the wrong way, and then things are difficult. In the second proof, it's just what you now find in the textbooks. Okay, and then if you look at graphs where you also have a linear order on the universe, but connectivity still doesn't refer to the linear order, but to the edge relation of the graph. So an ordered graph is connected if and only if its unordered version is connected. Showing that connectivity also on these linearly ordered graphs is not existential monadic second order expressible. That's really extremely difficult. And that was part of Thomas Schwentig's PhD thesis. So that's really, you use Ehrenfeucht-Bresset games and lots of combinatorics and lots of clever encoding ideas, and then at the end you get it done. So this, although the game looks so simple, for finding winning strategies for duplicator often requires highly non-trivial combinatorial arguments. And that's why we would like to make use of known results. So if we can avoid doing this difficult stuff and just reduce from known stuff like Fagin or Schwentig or whatever, the proofs often get much easier. And that's two things that I will look at next. So one is logical reductions, and the other one is locality results, which gives you like a black box saying, if you have this situation, then I have a black box saying you win the Ehrenfeucht-Bresset game. But let's first look at the logical reductions. So the idea is to use known non-expressibility results for showing new ones. And for example, to show that the property of being acyclic, so here I mean a graph being acyclic, so that a graph doesn't contain a cycle. That's not first order definable. So by Ehrenfeucht-Bresset games, you can do this game and find winning strategies, but it's much shorter if you just do a reduction. So if we say we already know that being a linear order of even cardinality is not first order definable, I want to use this to show that not being a cycle is not first order definable. And the proof idea is you do a reduction, so you assume for contradiction that being acyclic is first order definable. And then I want to change this formula, which tells me the graph is acyclic, into a formula which tells me a linear order has even cardinality. And the idea is, well, okay, linear order of even cardinality. I want to associate with a linear order a graph such that this graph can be defined in first order logic from the linear order, and such that this graph contains a cycle if and only if the linear order has the right length. And the idea here is that, I have a picture here. The idea here is, so if your linear order has 5 elements, A1, A2, A3, A4, A5, what you do is you view this as a graph where you say edges go from the largest to the smallest, and then you take every other vertex. And that's something you can easily define in first order logic. And here it's, well, if the length is odd, you have a cycle. And if the length is even, you don't have a cycle when you define this graph. And since you can describe this kind of edge relation in first order logic, what you do is you take your formula for being acyclic everywhere where you have the edge relation in the formula. You write the first order formula describing this edge relation. And this edge relation is described with respect to the linear order. And then you have your reduction. Okay. So, and this often works. So most of the things that I do in my introductory logic course, and I do a lot on first order logic there, I prove things about even cardinality of linear orders, then everything else is by reduction to this one. Okay, another tool in this toolkit is locality results. And here, it's easy to think about graphs. So for a graph, we have a concept of neighborhood. The distance between two nodes is just the length of a shortest path. And even when I speak about directed graphs, with the distance, I mean the undirected distance. So I don't care if I traverse edges in the wrong direction. And the ball of radius r around a node A, well, is just all nodes of distance at most r from A in this graph. So for radius 0, it's just the node itself. For radius 1, it's the node itself plus all its neighbors. For radius 2, it's all these plus all the neighbors of the neighbors, and so on. And if I use this calligraphic n, I mean the induced subgraph on all those nodes of distance at most r. Okay, now so there are two major locality notions. One is Geifmann locality, one is Hanf locality. And the way it's presented in the textbooks most of the time is that you have a fixed radius, which doesn't depend on the size of the structure. The notion that I introduce here is a variant of this, where the radius may depend on the size of the structure. And that's what f of n here says. So let's look at the definition. So when I have a tuple or a list of nodes, then the neighborhood around this tuple is just the union of the neighborhoods around the individual nodes in this tuple, and the associated subgraph. So now what is the definition? Let Q be a k-array graph query, and f is some function which tells me if I get a structure of size n, what is the radius that I'm interested in. And now a query Q is called f of n local. So n is the size of the structure that I'm evaluating the query on. If there is some n0 such that for every n bigger than n0 and every graph with exactly n nodes, the following is true for all k tuples A and B of nodes. So if the neighborhoods around A and B up to radius f of n are isomorphic, then A belongs to the query result if and only if B belongs to the query result. So it's so that's the notion of locality we look here. And what is known about this?
Can I ask one quick question? What happens if you have sentences?
This notion of Geifmann locality here doesn't make sense for sentences.
Okay, good.
So we will have a notion of Hanf. Yeah, exactly.
Okay, yeah.
So what you have in Geifmann locality is you have one fixed structure and then you look at nodes. And the idea of this locality notion is you have this graph, and then you have, so for arity k equals 1, if you have this node and you have that node, then you know if their local neighborhoods look exactly the same, then this node is in the result if and only if that node is in the result. Okay, and what is known? So, and these results are called Geifmann locality results. So from Hiller, Lipkin, and Norman, and in some sense also already from Geifmann's locality theorem, although Geifmann didn't view the theorem in that way, I think. It's known every graph query Q that's first order definable. For every such graph query, there exists a constant C such that the query is C-local. So this means no matter how big the graph is, I get a constant so that I only have to look at neighborhoods of this constant radius. And there was an extension by Grohe and Schwentek to, well, order invariant first order logic. So what does that result say? For every graph query Q that's first order definable on ordered graphs. So what does this mean? First order definable means you have first order logic where you use the edge relation. But on ordered graphs means you also can use a linear order, which has to be a linear order on the graph. But graph query means the result of the query should only depend on the edge relation and not on the particular linear order that you choose. And that's also called order invariant. So your formula can make use of the order, but the result of evaluating the formula should only depend on the edge relation of the graph. So if you extend first order logic by allowing to use also a linear order, but in a way that you only can that you have to be invariant for this order, then still you have the same locality result. There is a constant C such that the query is C-local. So then the next question is, well, here you can use a linear order in an invariant way. Why not also use the bit predicate? So if this linear order associates numbers with your nodes. So you can, in some sense, identify the nodes with numbers 0, 1 up to n-1. And then if you have these numbers, you can do bit representation of the numbers. You could do whatever you like. And that's something that some algorithms make use of when you do hashing or when you whatever. So why not give the formula the possibility to do that? And also when you think of database systems, these invariant logics in some sense might be reasonable, because when you store your database, you have stored things in some order, and you might even use with arithmetic of storage positions and so on. But then you want data independence, so you don't want that the query expresses something completely different when some maintenance work has been done on the database, so you want this invariant things. But if it gives more power to the user to express queries, why not? And it does. And now here we look at first order logic on graphs where you can use a linear order and then arbitrary numerical predicates. So linear order identifies your nodes with numbers 0, 1 up to n-1. And then arbitrary numerical predicates means on these numbers you might have addition and multiplication and bit predicate and I don't know, whatever you like. And we call this ARP invariant for arbitrary numerical predicates, but they have to be used in an invariant way. For every graph query Q that's first order definable in this way, there is a constant C such that the query is log n to the C local. So what does this mean? You can look, so the neighborhoods, so if the graph has n nodes, the radius of the neighborhood is polylogarithmic in the number of nodes. And here it's really known if you have addition and multiplication that you are not local if the radius is too small. So with addition and multiplication, you can construct instances where you get something where you can, what can you do? You can do reachability in certain cases of paths of length non-constant. So here you really have to have a radius that's not constant. If I wanted to prove the same thing as here, this simply is not wrong, is not right. So, but is this a usable locality result? Well, what do we use locality results for? I wanted to sell this to you as a means of proving non-expressibility. So by using this locality result, I can prove that connectivity is not definable in ARP invariant first order logic. Why is that the case? So what is to those who are familiar with this stuff, with this, it is almost everybody, you know this proof. How do you show that reachability query is not expressible in first order logic when using locality? So reachability query means you want to return all tuples of nodes such that there is a directed path from the first node in the tuple to the second. So if the standard example is the graph is a disjoint union of two cycles. The length of each cycle is n½ when n is the total number of nodes. And then what do you take? You take one tuple, A1, A2, that's this here. What does their local neighborhood look like? Well, it's the disjoint union of two graphs. What is the distance between these two? It's n/4, if this here is n/2. So, and if instead you take this node and that node, their local neighborhood looks just the same, but this tuple is in the query result and that tuple is not. So this query here is not n/5 local. This 5 here could also be improved a bit, but not n/5 local. So this result here tells you that if it was definable in ARP invariant first order logic, it would be log n to the c local. It isn't, so it cannot be defined. And essentially by using this result and all the known examples where you use Geifmann locality to show that something is not expressible in first order logic, you can use exactly the same proof and get that it's not expressible in ARP invariant first order logic. Okay, and in a few examples of that type are queries which ask, does node X lie on a cycle? If you use locality to show that it's not in FO, you use the same proof and show that it's not in ARP invariant FO. And all kinds of things. Is node X reachable from a node that belongs on a triangle? Or does node X and Y have the same distance to node Z? All this can be proven in that way. Okay, so how much time do I have? 20 minutes. So let me try to give you an idea of that proof. And the original proof of Geifmann locality of first order logic, you can do that with Ehrenfeucht-Fressé games, and that's what it's done like in Leonid's textbook. And I think, I'm not sure if it is it in the Ebbinghaus-Flum book.
No,
I don't. Yeah. 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 Okay.
Which my students could not understand. That's why I did it for myself.
Okay, so for first order logic, the proof is by Ehrenfeucht-Fressé games or by doing Geifmann normal form. For first order logic with arbitrary numerical predicates, I don't know how to do Ehrenfeucht-Fressé game winning strategies if you have arithmetic in your structure. I tried, and I know that several other people tried and failed utterly in constructing winning strategies. But what we can use here is results from circuit complexity. And that's, so there we have very strong results which we can just use as a black box. And that's what we do here. So what do I want to show? I want to show that for every query Q, which is expressible in ARP invariant first order logic, there is a number C such that the query is log n to the C local. That's what I want to prove. And the idea is I want to use known lower bounds from circuit complexity. And so what is the link to circuit complexity? So let's say Q is a query that's expressible by an ARP invariant first order formula. And then by Immermann we know that first order logic with numerical predicates are in some sense precisely the same as AC0 circuit families. And we take this and we will use this. Now assume that, so assume for contradiction that this query is not log n to the C local for any C. And what I want to do is I want to modify my circuit family to obtain an AC0 circuit family which computes parity. And parity means you get as input a bit string and you want to know if the number of ones is even. And for this we have extremely strong lower bounds from circuit complexity. And the one that we use here is from Hastad. So we don't just use that parity is not an AC0, but something that's slightly stronger that will do the job for us. Okay. So what exactly does Immermann's result, where you have a formula and associated with an AC0 circuit family, give us? So what we do is we represent a graph G by a bit string, and I write beta of G for the bit string representing G. And we just take an adjacency matrix for the graph and put the lines one after the other in the bit string, so the rows. And what else do? We represent a node of the graph by the bit string beta of node, which just has length n and has a 1 at the position I, where I is representing node A. So that's just the ordinary way of representing graphs and nodes in bit strings. But now, of course, I have lots of bit string representations. Namely, for every way I can identify the nodes with the numbers 1 up to n. And that's what I collect here, the representatives of G and H. That should be the set of all bit strings which correspond to all adjacency matrices of the graph. So all ways of embedding the vertex set of the graph into the numbers 1 up to n, where n is the number of nodes of the graph. So this rep of G and A is a set of all bit strings which represent the graph and the node A. Now, a unary graph query, Q of X. So unary graph query means it is evaluated on a graph and it returns nodes. Such a graph query is computed by a circuit family C if the following is true for all graphs, all vertices A of the graph, and all strings gamma which represent the graph together with the vertex. The node A is in the query result if and only if the circuit that's associated to this bit string representation. So for every input length we have one circuit which will compute on input bit strings of length n. So here we take the circuit for the right input length of this bit string representation and we check if this circuit accepts the bit string. And that's how you how you use circuit families to compute graph queries. And now Immermann's result precisely tells you that or a variant of Immermann's result tells you that a unary graph query Q of X is definable in ARP invariant first order logic if and only if it is computed by a circuit family of constant depth and polynomial size. You don't get anything about the uniformity of the circuit family, because here you have arbitrary numerical predicates, which also could be undecidable ones. So you don't get uniformity, but we don't need that here. Okay. So now how do we proceed? So let Q of x be such a unary graph query that's expressible in ARP-invariant first-order logic. And let C be the associated circuit family from Immermann's result. And here is a repetition of what we just saw from the definition. Now, for contradiction, we assume that this graph query is not log n to the C local for any number C. What does that mean? It means for every number C and every n0, there exists an n bigger than n0 and a graph with n nodes and two particular nodes, A and B, such that their local neighborhoods are isomorphic, but one is in the query result and one isn't. And what is the local neighborhood? It's the neighborhood of radius log n to the C, and that's what I'll call M from now on. So that here I just plug in the definition of log n to the C local, or not being log n to the C local. So this here is a counterexample to this locality. And to keep things in this proof idea simple, let's assume that these two nodes A and B are far away from each other, so that their local neighborhoods don't intersect and don't touch. Now the key lemma that we prove, and once we have this, everything is done by Hastad. The key lemma is that, well, if you fix some number M and some graph G and some nodes A and B in exactly the way we did here, and we have a circuit C that accepts all strings that represent G and A, and that rejects all strings that represent G and B. That's exactly the situation that we have here. A is in the query result, so my circuit accepts all string representations of G and A. B is not in the query result, so my circuit has to be consistent and reject all string representations of B and G. So if we have such a circuit, then we can modify this circuit into a circuit C tilde of the same size and depth that computes parity on M bits. So this M is the size of the neighborhood. And so once we have proved this key lemma, we are done. We just use Hastad's theorem, which tells you there exist numbers L and M0, such that for all M bigger than M0, no circuit of depth D and this size here, whatever this is, computes parity on M bits. And here you just plug in the numbers. What is M here? M is log n to the C, and then you do the computation, which I did here by choosing the right C, and here we compute a circuit that we construct a circuit that computes parity on M bits and whose size and depth are so that it's a contradiction to Hastad. So how do we prove this key lemma? So that's the key lemma once again. How do we prove this? So we have this circuit C, which, and I don't care about the query and anything anymore. I just want to use these things that are here on the slide. So we have this circuit C. We have the graph G and we have nodes A and B. And what do we want to do? We want to do something about parity on M bits. So let's look at an arbitrary string of M bits, and we want to know something about parity. And let's say our graph G looks like this. And we have the nodes A and the nodes B, and they are far away from each other. And then local neighborhoods are isomorphic. So local neighborhood, local means up to n. So these two things here are isomorphic to each other. Now I cut this into shells. So here the first shell is all neighbors of A, the second shell is all nodes at distance 2 from A, at distance 3, and so on. And so what do I do here? I look at this string, and I look at positions in the string where there is a 1. So let's say I is some number between 0 and I minus 1. So something here in this, so this is distance 0 from A, distance 1 up to distance m from A. So here I look at nodes between distance I and I plus 1. So what does this look like here? Maybe let's imagine you just have, let's make the picture a bit simpler. So in general, we don't know what the graph looks like, but let's say here you have A, here you have B, then these neighborhoods, and then here you have whatever, and here it's the same. And then there is, so that's 0, 1 up to m minus 1. And let's say here we are at I, and here we are at I. Now here you have u and v and an edge between u and v. And see, since these two things, these two neighborhoods are isomorphic, here you also have the edge. Now what you do is you just swap the edges. So instead of this, you do that. So you swap the endpoint of the edges, leaving the I neighborhood from A with the corresponding endpoints of the edges, leaving the I neighborhood from B. So what you have done here, so here I swapped the edges to obtain the new graph. And what does this look like? Well, it just looks like the old one. Here I just have switched these edges, and I've switched B and A. And now it looks like that. And I do this for all these positions where you have a 1. So if you have an even number of 1s, you have switched for an even number of times. If you have an odd number of 1s, you have switched for an odd number of times. So the resulting graph itself is isomorphic to the original one. But if you have swapped for an even number of times, the role of node A is the same. And if you have swapped an odd number of times, the roles of A and B have changed. And that's exactly what you do. And your circuit here can distinguish between A and B. And then you have to do mild modifications in the circuit to obtain the new circuit that where everything is wired in a fixed way that regards the graph, and only the stuff about here, this swapping of the edges, that will depend on the input string W.
Also, the inputs will switch on and off edges.
Yeah, exactly. And so if you want to look this up, I have a slide where I explain what this does, but I think it doesn't make sense to do this at the end of my talk. And I like this idea a lot of using circuit complexity results and just using them as a black box. Okay, so we had Geifmann locality. That's good for expressing that that some queries are not for proving that some queries are not expressible in some logic. Now, if you want to speak about sentences or properties or Boolean queries, Geifmann locality is of no use, but Hanf locality is. So what is Hanf locality? What is a Hanf local graph property? So now you have two graphs. In Geifmann locality, you just have one graph and two tuples. Here, you just have two graphs, and you fix some radius r, and you say that the two graphs are bijective. If there is a bijection between the vertex sets of the two graphs, and this bijection should preserve the isomorphism type of the R neighborhood. So when you look at some node A in the graph G, the R neighborhood of A should be mapped by this bijection to something that has an isomorphic R neighborhood in the other graph. And now the definition says that a graph property P is Hanf f of n local if there is an n0 such that for all graphs G and H of size n bigger than n0, the following is true. If G and H are f of n bijective, then G has this property if and only if H has the property P. So f of n bijective means you essentially the neighborhood types up to radius f of n occur for exactly the same number of types in the two graphs. That's what the bijection does for you. And now what is known about Hanf locality? So it is known by Fagin, Stockmeyer, Wadi, and well, by the original paper by Hanf, that for every graph property that is first order definable, there is some constant C such that the property is Hanf C local. So you only have to look at constant neighborhoods. And what else is known? Every property of strings or trees that is definable in order invariant first order logic. For every such property, there is a constant C such that the property is Hanf C local. So for strings or trees, we have Hanf locality also for order invariant first order logic. What would be nice to have is a Hanf locality for order invariant first order logic on all graphs. We don't have that. So that's one of the open questions. And it's not an easy one. What else do we know? So that's in the same paper where we showed this Geifmann locality up to radius log n to the c for ARP invariant formulas. But this result looks really weak. If you look at properties of strings, which you represent in the way exactly we did in the first part of the talk. So you don't have the linear order, you just have the successor. But now you can just use first order logic with the successor, so you can't define the linear order. But you look at ARP invariant formulas, then you can show that every property of strings that are definable in ARP invariant formulas in that sense, for every property there is a constant C such that the property is Hanf log n to the c local. And again, it would be nice to have the same result for graphs, but that's a long way to go. Yes. Yes. In the first case, it depends on the quantifier depth. In what does it depend on? I can't say at the moment. I have to think about it. So I'm sure that in the paper we had some more precise information. I think it also is something about the quantifier alternation, which in some sense is also there. So concerning Hanf locality, for first order logic, we have exactly what we want to. For invariant extensions of first order logic, we have something, but we don't have what we would really like to have. And I think that's the point where I should stop and go to the...
Can you maybe show us the example how that works? Not seeing that at all.
How that works?
Yeah.
So, what do I claim? The class of all strings of the form arbitrary number of C's, then an A, then arbitrary number of C's, then an B, and then arbitrary number of C's is not definable in ARP invariant FOs with successor. So, look at a string where you have a long sequence of C's, then you have an A, then an extremely long sequence of C's and a B, and again lots of C's. And swap A and B. So this is in the language, this isn't. Because my language says first the A, then the B. So this is a string which is not in the language. This is a string which is. Now, why are they equivalent with respect to these Hanf types? So what is the local neighborhood of A like? It's an A with lots of C's around. It's the same here. So you map this position to that position, and all these close positions to all these close positions. You map this to that, and then you have remaining positions where you just see C's in sufficient numbers. And then to make this radius the size you want to, you just take a huge number of C's here. So you see these two are f of n bijective for whatever f of n you want to have, almost. But one has the property and one hasn't, and then you get the contradiction. So let me finish just with a few open questions. So we looked at Geifmann locality. Here is a short version of the definition of Geifmann locality. What have we seen? We have seen queries definable in order invariant first order logic are Geifmann local with respect to constant locality radius. And if you look at ARP invariant first order logic, they are Geifmann local with respect to polylogarithmic locality radius. And what we can also show is that you really need this polylogarithmic if you have addition and multiplication in your ARP invariant stuff. But so there is one open question that's one of the exercises in Leonid's textbook. And I spent a substantial amount of my time in trying to solve this exercise. Yeah, I know. Do you have a list of which of these have been solved in the meantime?
At least two by Rossmann.
Yeah. So as far as I know, this hasn't been solved. So the question is, how about addition invariant first order logic? So you have first order logic, you can use the linear order and also the addition. So you associate numbers with the elements, numbers 0, 1 up to n minus 1. You have linear order on these numbers and you can use addition on these numbers. Of course, this falls into that. So it's Geifmann local with respect to polylogarithmic locality radius. But it's an open question if it's Geifmann local with respect to constant locality radius.
And it's more expressive than order invariant.
It's more expressive than order invariant. But somehow I don't even really have a conjecture. So I would try to prove this, but because I don't know how to use this addition to do something non-local, but I failed utterly. So if anybody has any progress, please let me know. And I can't tell you of any complexity theoretic consequences. So you won't get rich and famous when you solve this, but you will have solved a difficult question. Now, for Hanf locality, the situation is a bit different because we know much less there. So we have Hanf locality for first order logic, but then for order invariant first order logic, we don't have a Hanf locality result for arbitrary graphs. And my conjecture would be that there should be a Hanf locality result for order invariant first order logic with constant locality radius or with some sublinear locality radius. But all we have until now is that on strings or trees definable by order invariant first order logic, we have this Hanf locality, and already this Benedict-Ségoffin result, that's extremely difficult to prove. So don't expect to just sit down and solve this open question. And again, for ARP invariant, we also don't have a reasonable Hanf locality result on arbitrary graphs. So open question is, do these results generalize from strings to arbitrary finite graphs? Or maybe even to graphs of tree width at most k. I'm not aware of a result generalizing here Benedict-Ségoffin to tree width 2. Even that would be interesting. Okay, and then decidable characterizations. That would be really great. So are there decidable characterizations of order invariant first order logic, addition invariant first order logic, addition multiplication invariant first order logic? And in some sense, this quest for a logic capturing p time is the question if there is a decidable characterization of order invariant least fixed point logic. And maybe that is too big a step, but if you look at order invariant versions of smaller logics, which are less expressive, that's something where you can still do something. And what do we know? We know on strings and trees, order invariant first order logic is has the same expressive power as plain first order logic. So the strings I consider here is the.
I was like, because I think it's Niemist 1 year earlier. And he did it for counting as well.
Yeah,
Yeah, but Niemist proved it a year earlier.
yeah, we should ask Luc. And we have for addition invariant first order logic, we have a similar result on very uninteresting structures. So it's just finite colored sets with no edges and no binary relations. And also this was not an easy exercise. Okay, so you see in these locality results, they have been around for decades, but still there are interesting open questions. And thank you very much for staying the entire morning with me.